name is Tom Harper. I'm a DPhil student here at Oxford, but this is some joint work I did with Oxford at Utrecht University on implementing fusion in the Utrecht Haskell compiler. So just to get everyone on the same page, we're going to go through a brief example of what I mean by fusion and what exactly we're implementing in UHC. So this is a typical functional programming example, and a very typical one for fusion, which is the sum of squares. So we're generating an enumeration from 1 to n. We're squaring the resulting list, and then we're summing that list together. It is very nice because it's it sort of exemplifies a lot of features that we like about functional programming. In particular, we're taking some small, sometimes higher order functions, and we've composed them together to make it a more powerful one. It's very clear what's going on, what the programmer intended for, and at the same time we get a very short but sort of powerful program. But this does come at a price that we often don't talk about, and certainly you don't talk about when you first learn functional programming, which is performance. And in this case, so this is one way you can think about how this function is applied. So sum of squares is applied to 5. What first comes out is a list. It's a list of 1 through 5. After that is squared, you get the list of 1, 4, 9, etc., and that's summed up to 55. So what we actually have in the execution of this program are two lists. We didn't start with a list, we don't end with a list, but in memory somewhere, we took out memory for two lists. And this is bad for performance. Well, it's certainly bad for memory. It often translates into a performance issue. So before anyone asks, I will say laziness does mitigate some of this. So for lazy structures, you actually usually don't see 1 through 5 altogether. This list is unfolded slowly as needed, but it does still affect performance. So fusion is worth it, both for strict data structures where it's very valuable, and for lazy ones where it's a little bit valuable. So there is a way to get rid of these, and I can write this function by hand quite nicely. Nicely, I think it's pretty ugly actually. So this is the sum of the squares in a very imperative way. So what I've done is I've taken all of the features of the 3 recursive functions that were composed together, and I've put them into one sort of recursive loop here. So instead, I initiate a loop with 1. This is sort of a cursor. You can think it's a for loop. We say, have we reached the end yet? No. So square this number and then add it to the resulting recursive call. So of course, I've accomplished it for all, but I've got rid of all the functional programming part of it. Now I have a recursive function that's not particularly nice. No modularity, less clear, less maintainable. So where are we? Well, the goal of all fusion in this case is to write sum of squares and have the compiler produce a fused version automatically. This is, in general, this is really hard. Justifying transforming recursive functions is not something that you can just do arbitrarily. Depending on the nature of the recursion, etc., there are different proof obligations. So people have taken various steps to get around this, and one of the most common ones is noting that inlining and fusing recursive parts of functions is extremely tractable. And we as the programmer can remove some of the work from the compiler so that all that's left for them to do is actually fuse these non-recursive parts. And this is how stream fusion and fold-our build fusion work, for example. And if you're not familiar with these, I'm not going to go into an in-depth explanation of what they are. But this is how, so in a stream fusion case, to give a quick example, you have these functions appended with s. These are functions over streams. If you don't know exactly how that works, you can think of them as these are functions that the compiler can fuse because they lack recursiveness for the most part. In between them, we have these conversions that convert to and from this representation called a stream. And these are recursive and these are unfusable. So how do we get rid of them? Well, you'll note that we have stream after unstream everywhere. And this is because we've inlined these functions and this is what we get. We can remove these. And in GHC, this is done by something called a rewrite rule that lets you say, if you spot this situation, get rid of these. And the result is a nice stream pipeline. And there's some hand-wavy magic, which I'll get to. And you end up with the new function that is all fused. So the principle behind this, and the principle behind almost all fusion that you actually see in GHC and various libraries, this includes repo, for example, is non-recursive functions can be fused, the conversions can be removed if they get in the way, and the result is a single inline, is a single function that does everything that the original composed function functions accomplish. So this idea is quite powerful, and the same transformations accomplish the same thing for all different ones, regardless of the instantiation that you're using. So the transformations are roughly the same whether you use array fusion, full Darboux fusion, stream fusion. So there's some generality to be had there. So in GHC, this is done by the simplifier. So for people who don't know what the simplifier is it's a phase of the compiler that does all sorts of transformations, and they're all local transformations. So what it does is it goes through the program, it looks for patterns and transforms one to another. This is a sort of typical way that a compiler will do some optimization. But the thing is, there's no real guarantees in the simplifier about what is applied when or where, etc. So what happens in GHC is fusion is a side effect of these local transformations, which is great. It means we don't have to do anything. But it does only work if they happen in the right order. In particular, if functions are inlined, which is one of the things it does, before they can be rewritten away, then they won't be. So if stream and unstream, for example, sit there, they are inlined away, the remaining code will sit there, it won't be fused away, because all the rewrite rules have is names, really. Furthermore, you have to do some other tuning with inline fragments. And it's very fragile as a result. So anyone who's done this before has realized they've written a program, they may have assumed it was going to fuse, they look at the benchmarks and say, oh, that's not quite right. And then you end up going and looking at core, and you say, there's some constructors that shouldn't be there. Why are they there? And then you proceed to do some more tuning. And unless you are very good, Simon Marlowe, he's in the room, a lot of it is guesswork at some point. And you don't really know what the simplifier is doing, or in what order it's doing them in. So when I started this work with I was asked what UHC had, and he said, it does almost no optimizations. And I said, great, I don't have to worry about I don't have to worry about anyone else's work. I can do whatever I want. So I wasn't going to go and implement an entire simplifier, because that seemed, one, excessive, and two, the goal was fusion. The goal was not a simplifier. So the question I asked was, with a clean slate, can we implement an easier to use, more targeted, more predictable algorithm? And the idea was, I was going to sort of lift out what GHC does and actually do it in the way we want it to be done. So this takes the onus off the programmer to sort of contort the simplifier into doing this. So the first observation was the purpose of using all these fragments is to tweak the simplifier so that things happen in a certain order. Namely, functions we want to fuse are inlined, the conversion functions are not inlined, the rewrite rule has to fire, and then there's some other local transformations have to occur. Now you can see that. So yes, the only sort of interesting part of this is perhaps steps 3 through 5 happen quite a lot. So usually you inline some non-recursive functions, you perform some local transformations, and then you might do this again. Actually, this is also a bit burdensome sometimes because GHC uses a heuristic to determine whether to inline things or not. And this is because inlining does incur a cost, it can duplicate work, etc. The principle of fusion is that you assume that inlining these functions is worth it because you're going to get some new optimization out of it. So we really want to be able to say, if I want to fuse this, I know that in UGHC, I want to inline this function. So what are these local transformations? Well, there's actually 4 really basic building blocks that accomplish fusion in all of these cases, and they're pretty simple. So they're inlining, beta reduction, and 2 perhaps less well-known ones are case of case and case of known. So inlining is hopefully familiar to everyone here, at least in principle. If I have a let bound expression, I can replace the bound variable with the expression itself. So here, it's important to say there are no mutually recursive or recursive functions allowed in inlining. And I'm sure it's clear to everyone why, which is we could be here a long time if we start allowing that to happen. And that's also the principle behind why fusion works, is we are removing the recursiveness with the rewrite rules and letting inlining proceed. So what does inlining do? Inlining gives us opportunities for beta reduction. And what is beta reduction? Well, now that I have a lambda instead of f there, I can now just apply and substitute appropriately. So that's pretty simple. Next is case of case. So inlining very often brings about this case, and this is necessary for fusion and comes up in just about every fusion technique that exists. So what does case of case do? Well, let's talk about what actually happens here. The inner case evaluates the expression E1, it pattern matches against the patterns, and then returns some some Ri, which is then pattern matched against the patterns Q, and then something returns. Now the problem is that, as we'll see, there's some, it's not clear that that's happening syntactically. It's not clear that R is actually going to be matched against Q in the case pattern. What we can actually do is push one case through another, is usually how this is said. So what happens? So we now still have a case, we pattern match against E1, we look at the patterns, but then we pattern match, we explicitly say, well now this case is pattern matching R1 against these possible patterns. So what's interesting about this is, this exposes the actual place that we remove constructor allocations. So the case of known. So I'm going to go back for a second. Presume that, and this is very common, we match against constructor and P, and that R itself is an expression that uses a constructor. So it constructs a new value from the old ones. If that constructor is explicit, what we see is we know exactly what that constructor is. We, as the compiler, already know what pattern it's going to match. So why don't we just lift out that expression it's going to pattern match against and do the substitution? And so this right here is where the constructors are removed, because we can see at one point we are applying a constructor to some expressions that allocates memory cells for it, and now they're gone. So the front end is where I think the programmer feels the most niceness of this chain, which is we're declarative programmers. We don't like to tell the computer how to do something. We like to say, I want to do this, and you figure out how to do it. And there's no reason Fusion should be any different, because hopefully what we've seen is I've outlined a rather simple series of steps to do. And it should be quite easy for us to automate that if we know what the programmer wants. Now the problem is there's no way to tell the GHC simplifier, this is what I want. You just tell it how to do it, and you hope it does it. We hope you get what we want out of that. So instead, we introduce in UHC 2 keywords. And I know Haskell doesn't like keywords, so if it really upsets you, think of them as pragmas as well. Whatever you need to do to get there. Convert and fuse. So what does convert do? So convert lets you say, I have 2 conversion functions. These are like stream and unstream. And so that basically says for all S, replace stream after unstream S with S. So from a programmer's perspective, this is sort of a less powerful rewritable system. And this could be replaced with something more powerful. I wouldn't say this is fundamental to the design. This is just what I did to keep from doing too fiddly an implementation. And fuse. So instead of these pragmas, all I say is my final function, the ones in my library that I've written that I want to fuse, are going to have a fuse keyword. And so this says, when composed, try to remove any conversion functions, and then try to fuse. So from the front programmer's perspective, their work is supposedly done. They do this for their library, and they can say, now if someone uses this, fusion will happen. And for the most part, it turns out that's true. So for the back end, fusion is performed over UHC core, and actually, from what I said before, all these transformations are actually performed over core, which is a stripped down version of Haskell that's more like a lambda calculus. It's similar to GHC core for people familiar with it. It's not worth covering the idiosyncrasies of it. All bindings use lets, so anything with inline just has to worry about lets. All pattern matching uses case explicitly. In true UHC style, this was all implemented using attribute grammars. So if anyone wants to know what it's like to implement high-level transformations with attribute grammars, I'm happy to give you a tutorial on that. So steps 1 through 2 are removing conversions. So this step is, if a fusible function is applied to another, the assumption there is that there will be a rewrite multiplier. We don't really worry about cases where it's not. One of the principles is that the program transformation should only be concerned with the areas that we've targeted. I'm not really interested in, I was actually much interested in kind of protecting the rest of the program from this. This is one of the bases for Fusion in general that's been accomplished this way is we let the programmer write whatever they want in the rest of the program, but we only target a small subset. So the assumption here is quite clear. We're assuming that if we inline the original function the conversion functions appear immediately in the body. Again, this could be replaced by an algorithm that's a bit more aggressive about it. There's nothing in principle that would make this impossible. This was simply the choice made. And in fact, this is very often the case. This is not something that's particularly onerous for the programmer to deal with having to do this. This was a decision made because this is very often how fusible libraries are written. So the fusion itself, if an expression consists of a fusible function applied to any expression, we assume that it's worth fusing, and that is a reasonable sort of assumption. So what do? We inline and reduce any non-recursive functions. And now the conversion functions, we assume we remove them all. That can be removed. If they can't be, they can be inlined away and made part of the optimization. We apply case of case if possible. We apply case of known if possible. And if one of the local transformations is triggered, i.e. the three things before that, the fusion algorithm is recursively called on the transform sub-expression. So for people who want to know about termination, we are making the assumption here that inlining this does not cause non-termination. Now, for the most part, this is true because inlining non-recursive functions does not cause this. There are some pathological cases you can do this. It's true in GHC as well. They can be protected against in a similar way, which is we could simply say, okay, we will try and do this for 5,000 iterations, but if it really is going to not terminate, bail out. There could be some other more sophisticated way to do that, but our assumption is that inlining is terminating. Case of case and case of known, don't introduce cases where there's some circularity. Applying case of case and then firing case of known doesn't make a new case of case appear. So the algorithm does terminate there. Afterward, there's a lot of dead code that appears. Inlining makes for a lot of dead code. You either inline every instance of a function a programmer wrote, or in some cases you introduce some intermediate code that you then inline and is removed. And that's a big win as well. It keeps code size from blowing up. And logic declarations are tied to memory allocation in the core. So that does keep unnecessary expressions from being allocated memory. So the results, where we have fusion, we've implemented some other fusion as well, but for namely full-dar level stream fusion, fuse fully with this technique and quite reliably. The transformation does not impact other parts of the program. This is, to me, a key thing. And in fact, what you do end up with when you have a simplifier involves, you tune it. The tuning affects the whole program, which sort of goes against the philosophy of this kind of fusion, which is you're targeting specific functions. So here, once again, the intention of the programmer is made clear. They want to fuse these functions. They don't actually know better than the simplifier about everything. And so nicely, the programmer does not need to know the details of this inlining because really the process is quite predictable and automatable. So this wouldn't be a performance presentation without some benchmarks. So here you can see the blue is unfused directly recursive functions using full-dar build, which is what GHC uses for the list library, is in orange and stream fusion is in yellow. So for those who think these look a bit disappointing, as they sometimes do, these are lazy data structures. I didn't do this for the strict one. So we can often see the speed up is usually about 5 to 10%, if there is one. That's predicted. That's what I would expect. That's what is seen with other fusion libraries that fuse lazy data structures. You can see that sometimes fusion is a decimation. That's also that's a problem with fusion, not necessarily with UHD, although that obviously means we have more work to do or could spot more optimizations. The same thing goes for now. We've put in a consumer with full-dar. This is just some more benchmarks. Just to be clear, that the timing on the left has changed. This is because full-dar and full-del don't like really large lists. They tend to overflow the stack pretty quickly. So I use smaller lists here. Again, we can see some improvements, some not. I'm happy to talk to anyone about why this might be for specific given functions. But the take-home message is we have achieved fusion. It does constitute an optimization, not 100% of the time, but I'm not, part of the project wasn't to change the nature of how fusion modifies programs. So future work. I do think that this is an interesting approach. I haven't done, the algorithm itself is only taking what GHC does now. What we have done is made it a lot easier for the programmer because we've removed a lot of the bureaucracy. Could we do more with this? Now that we know what the programmer again wants, instead of the programmer telling us what to do with fusion, it would be nice if we could give them some feedback. it'd be nice to know, oh, you tried to put two fused functions together, and no fusion actually occurred. There was no case of known, for example. So you should know this. You don't have to go check the core. You can be rest assured, oh, it didn't give me an error, it fused. Or, oh, it sent me a printout that says, oh, this fused and this didn't fuse. It would be good if there was some feedback, although that's a bit less clear cut, because we have to figure out some heuristics and maybe suggestions, which from type system ones is not always the most helpful, but and a hard problem. And always more automation. This is still a somewhat labor-intensive task for the library programmer. It would be nice if we could automate this generation of these functions that are fusible a bit better. And that's all. I'll take questions.
I thought what you were going to tell us was if you just dispense with the beast that is GHC and work on a smaller, simpler compiler like UHC instead, you can provide the programmer or the library programmer with more control over which transformations are applied and when. And in particular, give them some way of specifying what order transformations should be applied in and so on. Your ordering is fixed in the...
It is fixed in it, but it works. So it works for these fusion techniques that are usually, in full development sort of a continuation passing style one, or in stream fusion you call the thing that came before you. For that, it works.
Right.
And this is what constitutes a very large array of fusion techniques.
So there's no great virtue in providing the ability to specify different orders because they're not useful.
Not for the kind of fusion that we've been using or talking about. Maybe if we do that, people can discover new ones. I'm sorry, just to point it out.
Did I understand it correctly that you, as a programmer, can write down that stream and unstream of S is S?
So you just write convert stream and unstream, and you get this effect. This is.
But what happens if a stream and unstream of S is not S?
As in, what if you want to write it as in?
Well, if it doesn't have this property, we know that.
So I have a paper about this from last year at Haskell Symposium. About the onus is on the programmers to make that proof. And one of the things that would be nice is if these kinds of proofs could be automated or could be warned. But at the moment, I don't.
But it's allowed to write it down.
Pardon?
It's allowed to write it down even though the property does not hold.
At the type level, it has to hold. So you have to replace an expression.
But I mean,
You have to replace an expression with an expression of the same type. But no, it doesn't check to make sure that that property is correct. And in fact, it doesn't in GHC reradicals either. I would consider that a very easy problem.
So that means that your program can go definitely wrong because.
Yeah. I mean,
okay.
I mean, no, in the sense that, I mean, you can shoot yourself in the foot with this. That's true. And you can shoot yourself in the foot whenever you do fusion. And there's a lot of research on the correctness of these program transformations because many of them hold only under certain circumstances. Many of them hold. Many of them change non-terminating programs into terminating ones. This is a sort of, I don't want to say fundamental problem of shortcut fusion, but it is one that we encounter.
Well, it's what the program is, not if it's in the compiler and the compiler knows that the property holds.
Right. That would be. I mean, that would be a great feature to prove that.
Another question: can you tell something about the amount of time it costs to do the?
So I haven't benchmarked the compilation itself. The benchmarks, for example, to compile were one large module. It wasn't it was a couple seconds extra time to do that. It wasn't a minute. So no, I haven't looked at the overall the total cost of that, but it hasn't been difficult or particularly large. It probably would be. If you were compiling lots of things, because this rather small time would add up. But.
Okay, let's thank Tom again.